Okay, so good morning, everyone. So I am assuming that most of the audience are students. So for experts, it may be a little bit boring. So let me start with apologies. I also would like this session to be interactive. Please feel free to stop me if you have any questions. I don't have to finish all the slides, so if you have questions, I will be happy to stop and discuss. Okay, all right. So now I'll be discussing nuclear spins today using NMR, and I'll be describing how we can use it as a quantum workshop. Okay, so in our lab, we have these two architectures, nuclear magnetic resonance, and we also have a small nitrogen vacancy centers in diamond. But today I'll be mainly discussing nuclear magnetic resonance. Okay, so um, let's start with this outline. So we'll discuss nuclear magnetic resonance in the beginning, and then I'll discuss what do we mean by NMR qubits, and I'll give some examples. I have chosen two examples. One is on quantum algorithm, and another is on quantum sensing. Okay, so here is the important slide. So if you understand this slide, I think that is the take-home message. So this has much of the summary of what we do. So here is a sample in the orange color. So that's the orange rectangle here. So that's about 5 centimeter long and 0.5 centimeter wide. So that's a cylindrical sample. And inside that sample, we have some compound, some chemical. Okay, so it could be any chemical. Usually, we take diamagnetic compounds. So diamagnetic means there is no net electronic magnetic moment. So the electrons all add up their angular momenta to become zero net angular momentum. So they are diamagnetic. So then we can focus on the remaining magnetic moments, which are essentially nuclear magnetic moment. Okay, and these nuclear magnetic moment, so they align in fact, they interact with the external magnetic field. So this blue background, so that is the magnet, that signifies the magnet. It's a cryostat actually, so which is housing a superconducting magnet, very strong magnet. It can be 10 to 20 Tesla. Okay, so it's a strong magnet, and so these nuclear magnetic moments interact with that magnetic field, very strong magnetic field, via Zeeman interaction. And if you take a spin half nucleus, for example, hydrogen nucleus is proton, and proton is a spin half particle. And so it will have two magnetic quantum number, plus half and minus half. So if you take plus half as parallel to the magnetic field and minus half as anti-parallel to the magnetic field, and there will be an energy gap. And so that is the Zeeman energy gap, which is proportional to the strength of the magnetic field that you apply. It is also proportional to the strength of the magnetic moment. So for a given nucleus, say a hydrogen nucleus, so you have specific energy gap. If there is carbon-13 nucleus, you have another energy gap, and so on. So now you have this energy gap, and so now that is fixed by the external magnetic field. And now what you can do is you can induce resonant absorption. So that can be done by an electromagnetic wave which matches with this energy gap. And for the fields, the magnetic fields that we apply, the energy gaps are such that this electromagnetic wave happens to be in the range of radio waves. So radio waves happen to be in the resonance region of this nuclear spin energy gaps. So typically it is like a few hundred megahertz frequency of radio waves. So then what we can do is, using such resonant radio waves, we can prepare quantum superposition of these states. Instead of only up and down, we can prepare quantum superposition of these states. So what we are going to do is, we will call this parallel state as 0 qubit and anti-parallel as 1 state of the qubit. So you can see that now we have a binary quantum system. So that's a quantum bit or qubit. Now, using this radio wave, we can prepare any arbitrary superposition of these two levels. And so that's depicted here. And that can live for a long time. In fact, it can live for hundreds of milliseconds, sometimes several seconds, sometimes even exceeding minutes. And there are special cases where it can live for hours. So, so that quantum superposition of nuclear spins, they are amenable to quantum control because of two things. One is their extraordinary long lifetimes of the superposition, and secondly, their precision control by these radio wave pulses. Not only that, these superpositions, they can give rise to signal. So signal comes out in the form of induction by these coils. So in the magnet, we also have coils. So these coils, they can they act like antenna. They receive signal from the nuclear spins. They get very characteristic signal from depending on the state of the spin system, and that is amplified, digitized, and sent as NMR signal. So that is the nuclear magnetic resonance. So you have nuclear spin in the magnetic field with the resonance RF pulse. So we can prepare arbitrary superposition and get signal out of them. So this is the overall summary of the nuclear magnetic resonance quantum workshop. Okay, so now with the modern spectrometer, it is like this. So we have this is the pictorial diagram. So we have this cryostat. We have central the probe housing the sample, and surrounding that there is a superconducting coil immersed in liquid helium, and surrounding that there is a liquid nitrogen, and then it's all sitting inside a vacuum chamber. So that's the NMR setup, and this is a panoramic view of our lab. So we have 6 NMR spectrometers. Okay, so NMR has applications in various fields. As you can see, it has been there for last several decades. It's about 7-8 decades, and so it has proven its important applications in chemistry, biology, physics, even in medicine. In fact, all the MRI machines, they are all based on NMR principles. In fact, they are just NMR where samples are humans. So that's the MRI spectrometers. Okay, so now let me straight away come to NMR qubits. So I am sure in this series of lectures that you are taking, so you have already become experts in quantum information. So as you can, so this is just to just for the sake of completeness. So as you know, we have block sphere representation of a single qubit, and we have poles representing the basis states 0 and 1, and any arbitrary state is any arbitrary pure state is represented on the surface of the block sphere. And using nuclear spins, our goal is to be able to prepare all these any of these states that we need. Okay, and not only that, the whatever superposition states that we prepare, they must live for a long time, and we should get signal from these two states. And using that, we can do many things like quantum computing and quantum simulations and so on, which can show advantages over the classical computing devices. Okay, so let me straight away come to the nuclear spin workshop. So as I said, we are taking some compounds, and these compounds have molecules, and in each molecule we have several atoms, not just one atom. We have several atoms, and each atom has several. Each atom has nucleus, and so together we have several nucleus in each molecule. And so we can prepare a superposition state of each nucleus. And good thing is within a molecule, all these nuclei, they are all interacting. So that is what makes us, gives us a spin system. It is not just a single spin. It is mutually interacting set of qubits. So that is what we are going to utilize, because it is not enough that we have just a single qubit superposition. We should be able to do qubit-qubit interaction so that we can do non-local gates. And that is possible because all these nuclear qubits, they can interact with one another via either indirect spin-spin interaction or direct dipolar interaction. It is like magnet interacting. So that is the dipolar interaction. So they can interact with all these interactions, and that allows us to do qubit-qubit non-local gates. So in general, if you take a multi-spin system, so they live in a large Hilbert space, and then there is some specific initial state, and we can, using these RF pulses, we can design the quantum control such that quantum control is basically sophisticated quantum gates, such that we can drive the initial state from any point to any other point, so to another target point, very precisely and in a robust way. So that is the whole job of quantum control, that we should be able to drive the quantum system to very high accuracy with very high precision to a desired target state. Now, so this is an example slide of various qubits. For example, if you want 2 qubits, you can take these molecules. So the spins that are used are shown in pink color. So you can see that in this molecule, there are 2 hydrogen spins, which are protons. So each proton is a qubit, and they are interacting via indirect spin-spin coupling, also called as J coupling. So we can use this molecule or this molecule or this molecule. Here there is 1 hydrogen and 1 carbon, and carbon 13 is also a spin-half nucleus. So that also acts like a qubit. And in this case, it is hydrogen and phosphorus. For example, here it is 3 fluorines. So they all fluorine 19 is a spin-half nucleus. So now they form a 3 qubit system. Here, hydrogen, carbon, fluorine, together they form a 3 qubit system. And in this last picture, it is a 7 qubit system, and so on. So there are more qubit systems. So for example, this we showed as a 12 qubit system. This is L-histidine, and this is another 12 qubit system. And recently we showed a 38 qubit system and demonstrated quantum battery. Okay, so there is a central silicon. There are 2 silicons side by side, and there are 36 hydrogens here. So together we can they act like a charger battery system, which we can control. In fact, we can charge the battery, and battery in this case is the central silicon, and then it can give the energy to a peripheral silicon, and that acts like a load. So all these hydrogens, they act like chargers. Okay, so I hope that gives a rough idea of the architecture that we are talking about. So there are molecules. Inside the molecules, there are nucleus, and these nucleus interact with the external magnetic field. And so if they are spin-half nucleus, each of them acts like a qubit in the presence of the magnetic field, because they have non-degenerate spin states, and which can be controlled very precisely by radio waves. And so we have quantum systems, 2-level quantum systems, and which can be controlled by external RF field, which acts like which forms the quantum gates. Okay, just to give one example, how to make a C0 gate. Okay, so I'm sure you have now already studied control NOT gates, how to prepare a C0 gate. So in this case, we will have to apply a set of RF pulses, which are shown by rectangles here. Each rectangle here corresponds to one particular pulse. So blue rectangle corresponds to X pulse. Okay, so this is pi by 2 pulse along X axis, and red rectangle corresponds to pi by 2 pulse along Y axis. So now you have pi by 2 Y, and now you have this line connecting these. So this is the interaction that I was talking about. So that's the J interaction, the indirect spin-spin coupling. So we have to let this interaction take place for particular duration of time, that is T here, and J is the strength of the interaction, and this is Ising type of interaction, ZZ interaction between the two spins. So this is already built into the spin system. We don't have to do any specific things for this, because every molecule, if you see the spin system, which are nuclear spins, which are close by, they are already having this built-in J coupling. We just have to measure them accurately and then let them evolve for certain time, such that this forms this the rotation about this ZZ operator should be this 3 by 2J. And then again we do these, we apply these set of RF pulses resonant on hydrogen in the top row and resonant on carbon in this bottom row, and together you can prove that this forms a C0 gate, control NOT gate. Okay, so that is just to give an example of how quantum gates can be applied. As you can see, this gate is now the x-axis is time. It is, we are applying in a temporal way. It is not like space based. So ordinary logic gates on semiconductors, you know, there is a NOT gate which is etched on the chip, and it's all, it goes, it flows in space. Of course, there because it flows in flows by step, it is also time wise, but here it is x-axis is time here. So we apply one pulse after another pulse, and in between we may have to let the spins interact with one another. So together we can form a quantum gate. Okay, so now that is the first part of the talk, and I just want to know if there are any questions. I can stop for a while if there are any questions. Okay, so if there are no questions, then let me continue. I'll just give two examples. So one is about quantum algorithms, and then I'll go to quantum sensing. Okay, so just to give one example, so let's consider this example by Chong on factoring. So this is the first experimental demonstration of Shor's algorithm. So this was done 25 years ago by Chong, who is also the author of Nielsen and Chong book. So what they did was they used the C0 gate that I showed before, and so you see we can implement Shor's algorithm using phase gates and using control OR gates and using some local gates and so on. So that's exactly what they did, and they could factor the number 15 into 3 and 5. So, but what I'm going to describe today is slightly different. So instead of applying Shor's algorithm, there is another algorithm that is called adiabatic algorithm. So adiabatic algorithm is a very general algorithm where the objective is to reach the ground state of a given Hamiltonian. And it's a non-trivial problem. You know the Hamiltonian, but you don't know the ground state. The goal is to reach the ground state. Okay, and the ground state contains the answer. So you start with some known initial state, which is not necessarily a ground state, and you know the Hamiltonian, okay, but you don't know the ground state. Okay, so that's the adiabatic algorithm. But the problem is there are two problems here. One is, given a composite number, how to find the corresponding Hamiltonian. Okay, so that's a different problem. So that can be okay, so that can be found out classically. We have shown how to do that before. There are different papers on that. But what we are interested today is in the second part. So suppose the Hamiltonian is known, how to find the ground state, and from there how to find the factors. Okay, so that is described here. It's a busy slide, but I hope I'll be able to give you some gist of this. So the idea is first to prepare some initial state. This is a known initial state. Okay, so specific initial state. This is independent of the factor or composite number. Okay, so this is a fixed initial state. In this case, okay, so here the circuit shows it is 0, 0, 0. Okay, so that's the initial state, and then you have to apply Hadamard on all these things, and then the Hamiltonian is known. So you have to start this adiabatic evolution. So what we do is the following. So we take we start the system in some beginning Hamiltonian, so H0 for example, and adiabatically, that means very slowly we change the Hamiltonian to the target Hamiltonian, and target Hamiltonian encodes the factors, okay, in the ground state. So that can be done. Its details are bit lengthy. I will not be able to cover today. So, but that can be done by changing some parameters. In this case, as you see here, it is the S parameter. If you change S parameter, Hamiltonian changes from initial Hamiltonian to the target Hamiltonian. Okay, and it has to be done slowly because it has to be adiabatic. We have to avoid all the transitions during this process. And if you do slowly enough, and then you reach the final Hamiltonian, and once you reach the final Hamiltonian, you measure. Now here are the results of the NMR experiments. So as you can see, the initial state has all these spectral lines, and now 0, 0, 0. Once you prepare this 0, 0, 0 state, so you can see that this is 0, 0, 0. So there are 3 transitions. So they correspond to 0, 0, 0 state. And then you carry out this adiabatic evolution, and finally after adiabatic evolution, and then finally you apply this final Hadamard gate and measure. Finally you get this kind of transition. So there is down, up, down, up, down, up. And so if you find out what are the states they correspond to these specific states, and that is 0, 1, 1 and 1, 0, 0, and those are the ground state, because initially you started with the ground state of the beginning Hamiltonian. Since the evolution is adiabatic, the system always remains in the ground state. So finally you reach this Hamiltonian that encodes the factors. You are still in the ground state. So the job is now just to measure the ground state. If you measure the ground state, you get these. So 0, 1, 1 and 1, 0, 0. And we have taken, these are experimentally implemented using this molecule. There are 3 qubits here, hydrogen, carbon and fluorine. And they have these specific interactions between the qubits. So for example, hydrogen fluorine interaction is 49.7 Hertz. Fluorine carbon interaction is 310 Hertz and so on. Okay, so now what these states, we got 0, 1, 1 and 1, 0, 0 in the ground state, what these states correspond to. And if you now, if you call this as P1, P2, P3, and if you sandwich between bits 1 on both sides and form this string 1, P3, P2, P1, 1. Okay, so why we have to do this specific way is described in this paper. As I said, that's a bit lengthy, but it's a general method. You can use it for any composite number. If you do that, then you get 29, and this corresponds to 19. So if you sandwich these two numbers between 1 and reverse the order, these two correspond to and convert from binary to decimal, you get 29 and 19. And you can confirm that these are the actual factors that we are looking for the number 551. So the Hamiltonian that we encoded was for 551, and so these are the factors that came out. So they come out with higher probability. So as you can see, since it is a adiabatic evolution, so these two numbers, once they reach those numbers, once you reach the ground state, it stays in the ground state. So for last 15 iterations, these numbers stay. So they just saturated those two numbers. So those two states. So that is, I know this is not very detailed, just to give overall just a flavor of the experiments that we do. Okay, so now we can do many things. So for example, just to give another algorithm, this is called benchmark quantum algorithm using these 12 qubits. There are many carbons, hydrogens, nitrogen, and so on in this molecule. All these spins or spin half particles, all these nuclei are spin half. So each of them is a qubit. And so each of these rectangle corresponds to very specific rotation implemented by the radio wave. The resonant radio wave on carbon 1 is in this row, carbon 2 is in this row, and so on. So you see, by tuning the resonance frequency, we have addressability. So if you tune the resonance frequency to C1, only C1 gets affected. If you tune it to C2, only C2 gets affected. So like this. And then in between, there are spin-spin evolutions. Together, we can implement this benchmark algorithm, and it involves entangling all these 12 qubits and then disentangling and seeing how much was the lifetime of the maximally entangled state and so on. So that is this 12-qubit benchmark algorithm. Now, so there are different registers. So we can go for larger and larger registers here. So as I said, we have demonstrated 38 qubits. But there is another way that we can realize hundreds of qubits, even thousands of qubits. That is via solid state crystals. Okay, so if you take crystals, you know that there are Avogadro number of spins. So they are all interacting. It is not like molecules, like a small molecule which has finite number of spins. Here, there are Avogadro number of spins. Now, I'll be showing some examples. So these spins, they have been used for a variety of applications related to quantum information. For example, in the year 2006, such crystals were used to study decoherence. So what happens when you have hundreds of thousands of qubits interacting, what happens and how the decoherence scales, and very interesting problems. So these are very useful. They give very useful insights into the physics of quantum information. Okay, so again, let me stop for a minute. If there are any questions, please feel free to unmute and ask questions. Okay, so if not, let me continue.
I have
yes.
Yes. I have two questions, probably three. Allow me to ask. So what are the fundamental scalability bottlenecks in NMR quantum computing?
Yeah, so as I said, there are indeed scalability issues. For example, so that's what I have shown here. In this y-axis, there is control, and this x-axis is register size. So we can say that as you increase register size, this way of molecule, there are different types of taking realizing NMR quantum registers. So what I have shown here is molecule-based. In the molecule-based systems, control becomes very difficult beyond a certain stage, as you see that these pulses are already getting crowded and they start interfering with one another. So the qubit selectivity will be lost soon, okay, as you scale more and more. That is one, and another important bottleneck is the ability to initialize all these states in specific initial state. For example, you want to bring all these 12 qubits to zero state. That comes with a cost in NMR. So the cost is that you lose sensitivity, and that's a big bottleneck. And so these are the issues. So we don't say that NMR will at least at the present technology will become a large scale quantum computer, but it is very good quantum workshop, and that's why I have titled my talk as quantum workshop. If you want to study physics of quantum information, it is very handy and very convenient.
My second question, can we use qubits instead of qubits, and this may help to reduce size of required qubits and their effective control?
Exactly. This is very good question, and in fact, this has been done since long time. So, for example, instead of taking spin half nucleus, so nuclear spins can come in any spins, right? It can be like a spin half integral or integral, and so on. So, for example, if you take lithium 3/2, lithium 7. So, if you take lithium 7 atom, its nucleus is spin 3/2. Now, spin 3/2 has 4 levels, right? And so that acts like a 2-qubit system because it has 4 levels. And if you take cesium 133, that is spin 7/2. Its nucleus is spin 7/2, and that will have 8 levels. And so like -7/2 to +7/2, right? -7/2, -5/2, and so on up to +7/2. So that has 8 levels, and that acts like a single nuclear spin, acts like a 3-qubit system. So these things have been demonstrated, and they indeed work actually. Yes, they act like qubits. In fact, if you can also take deuterium, for example, that's a spin 1 nucleus. Nitrogen 14 is a spin 1 nucleus. So all these things act like qubit.
Thank you.
So because they have 3 levels.
Thank you.
You said you have 3 questions.
The third one was related to the errors. So how effectively we can manage or control those errors? So I think this was already covered by you when you talked about controlling mechanism, but error issues, I think how effectively we can manage those errors.
Yeah, so that is the job of this quantum control. So that's why I am showing. What happens is, suppose in this example, you want to start from this initial state and reach the target state. However, because of errors, you may take different path. But now robust quantum control is such that even in the presence of errors, even if there are errors, at the end of the day, you should still reach the target. And that is the job of this optimal quantum control, and that is done by something called pulse engineering, and it's a very interesting field of research. Many people are spending a lot of time on this. For example, there is a famous scientist, Naveen Khaneja, Professor Naveen Khaneja in IIT Bombay. He has made landmark contributions on these, and here he has developed a new way of pulse engineering. All these pulse engineerings, they help us to mitigate errors.
Okay. So when you have written long living coherence, so does it mean that we can manage the decoherence by using some mechanisms or
yes, so there are ways you can extend the coherence times. So for example, there is something called dynamical decoupling, where you suppress the interactions with environment, you keep interactions within the spin system, and there are something called decoherence free subspace. So that means you always work within that subspace which is less prone to decoherence. So there are
So
error
it
correction
will,
methods, yeah,
yeah.
and so on. Yeah.
So, okay, thank you.
All right. Okay, so let's continue. All right, so let me just give this in the next 15 minutes or so. So let us discuss this problem of sensing. As you know, this is a very important problem. In fact, National Quantum Mission has dedicated an entire theme on quantum sensing. So the basic idea is measuring the world. So there is some quantity, physical quantity. It could be magnetic field, electric field, temperature, or pressure, and so on. And you have some probe. So there are two paradigms, classical and quantum. So in the classical case, you have a classical probe. So it could be coil, resistor, or cantilever, photodiode, whatever it is. And then this probe records some response due to these physical quantities. So it could be coming out as voltage or current or displacement and so on. And these are amplified and they are processed. And now what you are interested in is what is the limit on the precision. So what is the best precision you can get? And so there is something called the standard quantum limit. So that is the best precision you can get from classical systems. However, in the case of quantum, you can go beyond that. So what you can do is instead of classical probe, you have quantum probe, and you let that system evolve under quantum evolution under these fields. So now you can apply suitable quantum control and read the suitable signals, basically measure suitable observables. And then again, there is some signal processing and you get better precision. Why better precision? Because in the case of classical probes, and normally the phase information is not recorded normally. So it is mostly the amplitude information or intensity that is recorded, not the phase information. In quantum, not only phase information is recorded, but it is also using this constructive interference. And of course, if you take many-body quantum sensing, there is also entanglement that plays a crucial role. And these coherences, including this entanglement, so they allow you to get better precision. In fact, you can surpass the standard quantum limit and you can go to a new limit called Heisenberg limit. So that's the idea. So this sensing is a very important problem. So we wanted to understand the physics of this quantum sensing. Just to give one slide introduction how the quantum sensing work. So imagine a Bloch sphere like this. Okay, so you have a state which is now prepared along the x-axis. This is just the superposition of two qubits, 0 plus 1. And now you have a field, very weak field. And if this state is very sensitive enough, then that evolves under this weak sensing field, and then it gets a relative phase. So the state goes to another point on the equator, and so you get a relative phase. And now that relative phase is to be measured. And so once you measure that relative field, relative phase, from that you can work out what was the field that you wanted to sense. So that's the simplest example, but in general, the problem is the initial state can be an arbitrary density matrix rho 0, and due to the sensing field, it is getting transformed into rho phi. So rho phi is the encoded state. That is the state which is encoding the properties of the field that you are sensing. Okay, it can be encoding the direction of the field, magnitude of the field, and so on. So now the important question is what is the best precision you can get in this setup. So in order to understand all the physics of what are the various practical aspects. So for that, NMR is a very good test bed, which I am going to show in the next slides. So there is a very important, very fundamental notion. This is called Fisher information. And Fisher information is the distance between the initial state and the encoded state. In the previous slide, I described these two states. So there is an initial state, and after sensing field evolution, you have this encoded state. And Fisher information is roughly, it can be described as the distance between these two states. And now the error I was talking about, if you describe in terms of variance, and that happens to be is inversely bounded. So the lowest error that you can get is 1 over f. That's the Fisher information. And here just nu is the number of repetition. And this inequality, that lower bound on the variance is 1 by nu f. So that is called Kramer-Rao bound. Okay. So now okay. So before we go further, just to keep this in mind, I'll come back to this again. So now what is the idea here is that we are going to use many body sensing. Okay. So in this many body sensing, so there are multiple qubits. In this table, I have shown 4 qubits. So they can, I have also given 4 states in this example. And say, for example, in this first state, it is 0011 plus 1100. So this is an entangled state. And if you calculate, okay, so this is another notation. This is 2 qubits in 0 state, other 2 qubits in 1 state, and so on. Okay, so this is another, this is called excitation notation of the same state. It's the same state in different notation. Now here there is A and B here. Capital N is 4 because it's a 4 qubit example, A and B. And if you calculate this quantity A plus B minus N, that is called coherence order. So that's what here, that's a coherence order. Now that is Q. Okay. Now for different states, coherence order is different. Here it is 0, here it is 1, here it is 2, and in this state 0, 0, 0, 0 plus 1, 1, 1, 1. So that is having this coherence order 4. It's also called as a noon state. Now what happens is under this sensing field again, so instead of that single qubit example I showed before, if you use now these many body quantum systems, 4 qubit system, then again you get a relative phase between the 2 basis states. However, you get a factor Q in the exponent now. So you see that the evolution is now amplified by the factor Q.
So sorry, the content of your slides is blurred. Now it's clear. Yeah.
Now it's clear. Okay.
Yes.
All right. Okay.
Could you go to the previous slide, please? I think it was very difficult to. Yeah. Now it's okay. Thank you.
Now it's okay. 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 Great.
Yes.
Okay. Okay. So so what I want to just give a summary in, I think I may have next 5 minutes or so. So is to convey that this sensing is a very interesting interplay with many things. So in this diagram I have showed here, illustrated, that there is some quantum system prepared in some specific initial state, that is rho 0. So that's the quantum system. It's in some specific superposition state. And there is sensing field. And now there is noise being applied. I mean, noise is ubiquitous. Noise is always there. The noise is coming from the environment. And then there is a control field, because you want to control the evolution in a certain way, and you want to prepare certain specific initial state. So there is a control field. And also there is a very important thing is there are specific observables that you want to measure. Okay, so all these things are important, and so that you can maximize the quantum Fisher information. And if you maximize Fisher information F, you get minimum variance in the parameter. So that's the idea. So now what you do in many body quantum sensing is you prepare that n-qubit probe in specific initial state rho 0, and here entanglement matters. As I shown, noon state is most sensitive in the previous slide because it has maximum coherence order Q, and so entanglement matters. And you want to encode the sensing parameter phi in the density matrix, and and then let that evolve for some time under the sensing field, because it has to get itself encoded. The quantum system should get itself encoded in the sensing field over some time tau. So this tau is important. It could be sometimes long, such that the lifetime of rho matters, because if this quantum state is very sensitive, but if it is not long lived, then it is not able to capture that sensing field. It is not able to get itself encoded. So this lifetime of quantum state is also important. And of course, now we have Kramer-Rao bound. So Kramer-Rao bound again depends on the quantum Fisher information, and quantum Fisher information scales as the number of qubits as well as the coherence order. And so that is the Q is also important. Coherence order is important. Larger quantum system in highest coherence order, they give best precision. So that's what quantum Kramer-Rao bound says. And you have to measure right observables. You have to choose the right POVMs, and then you get the signal. So observables matter. You see, there are many things, and it's a complex interplay of all these things which give rise to best sensing. And so this is not experimentally studied in detail. So we decided to study this problem. But then small scale demonstrations were already there. Hello.
Your slideshow is not visible.
Again?
I can see your slide.
I'm not able to see it. I don't know.
So entanglement assisted metrology, I think
you can see, right? Entanglement assisted metrology.
Yes, I can see.
Yes. Yeah. So I was just saying that this many body sensing is not very well studied in experiments. And so, for example, many body means taking many large entangled systems. Okay, so that's what we were interested in. For small scale demonstration, it has been there already since long time. For example, David Corey's group from MIT, they have demonstrated this entanglement assisted metrology 20 years ago, and they found that they can reach Heisenberg limit. Even this was demonstrated in 2009. They showed that instead of many C0 gates here, you can use just single C0 gate using a symmetric system like this. This was shown by Jonathan Jones from Oxford, and they showed that using such NMR systems, we can get to micro Tesla sensing. And in fact, you can go beyond the standard quantum limit and can reach the Heisenberg limit. So this was already shown. But still, the complex interplay between all these factors in large registers, that was missing. So that's why we started looking at this problem using single crystals. So if you take a single crystal, there are a large number of atoms, and there are Avogadro number of atoms, and they're all the nuclear spins of all the neighbors. They are all interacting via dipolar Hamiltonian. So this is the dipolar Hamiltonian, and so they're all interacting, and so it's a very interesting system actually. But only thing is, you don't have individually addressable system. You have globally addressable system. You can't address individual nucleus depending on the space. But globally you have control, and you can get global measurements also. But then there are some interesting possibilities. So if you take plastic crystal, for example, in the case of, so that's what we do. In the case of plastic crystals, molecules spin in their equilibrium positions. So they have translational order. Molecules are in specific translational positions, but there is no orientational order, because even at room temperature, they are spinning in arbitrary orientation. And so that is very convenient, because this is quite popular in NMR field, because they have long coherence times, and so they are very interesting systems, because they have large number of spins. They still have large coherence times. And using that, there have been many interesting studies made. This is quite long, 40 years ago. These people have shown that using such systems, we can realize. Just a second. Anand, can I call you later? So using such systems, we can realize this Hamiltonian. This is called double quantum Hamiltonian. This is plus minus minus. Now, what is the property of this double quantum Hamiltonian? The double quantum Hamiltonian prepares entanglement. So it starts entangling qubits. Okay, it starts entangling with neighbors. So each qubit gets entangled with neighbors, and that entanglement size grows over time. And so what happens is initially, so I can show you. So initially you start with all unentangled qubits, and slowly they get entangled.
Hello?
And hello, yes.
Yeah, hello, sir. You have just
Yes.
5 minutes left. So
Sure. I am almost done. Yeah. So now they get entangled, and you can also measure the size of the entangled cluster. So you just have to, so each rectangle here is again an RF pulse, and you have this correlating set of pulses that is applied repetitively for L1 times, and uncorrelating set of pulses that is applied for again L1 times, but uncorrelating pulses are applied with a phase shift phi. And now you apply final Hadamard gate and then measure the signal, and that gives like this Gaussian type of signal. And if you measure the width of the Gaussian, that is related to, so that is delta is the width of the Gaussian, that is related to size of the entangled cluster. Okay, so 0.36 times delta square, so that gives the entangled cluster. For example, now for L1 equal to 6, if you apply this set of pulses for 6 times, you get to length, the size of the cluster as 100. If you apply for 10, it is 1000. If you apply for 14, it is 3000. So you see 3000 qubits are entangled now if you apply L1 for 14 times. So now you have large entangled cluster, and now if you start doing sensing, what happens? In fact, it was used for studying decoherence back in 2010 by Dieter Suter and so on. So they found very interesting results for such large entangled clusters, what happens under decoherence. So what we now do is use them for sensing. Instead of applying ideal pulses, now we apply noise now. So if you apply noise, now the question is whether this noise has effects on the signal, on the Gaussians that we saw. So ideally we have this Gaussian profile, and under noise, now our question was this, whether the variance continues to goes on increasing with the size of the cluster, or is there any optimal coherence order? The reason why we wanted to check this is as the coherence order increases, the size of the cluster is larger and larger, they become more and more sensitive. However, lifetime decreases. So there is a competition. So lifetime is also important. Size of the cluster is also important. But as the size of the cluster increases, lifetime decreases. So there must be an optimal coherence order. So where the variance is maximum. And that's what experimentally we found recently. And we found that depending on the noise that we apply every time, there is an optimal coherence order. So that means even larger clusters, they are not useful because they are not having long enough lifetime to encode the sensing field. So using such methods, we can now prepare states which are very sensitive. In fact, they are sensitive to jitters of 5 nanoseconds, and they can capture such fields. Okay, so now with this, let me summarize. Nuclear magnetic resonance involves taking molecules or solid state systems in strong magnetic field, and then we apply resonant radio wave as shown here, and so we can realize quantum dynamics, very interesting and very precise dynamics that we can realize, and then we can measure the states in the form of nuclear NMR signals, and from that we can study the properties of the spin system as well as the properties of the algorithms or the physics of quantum dynamics. Okay, so thank you very much. If I have time, I can take a few questions.
Yeah, Mahesh, I have one question.
Yes, yes.
See, for example, this kind of system, so you are able to detect jitters of the nanosecond kind of things, right?
Correct, yes.
So would it be sort of sensitive for gravitational wave kind of thing? No.
So actually our setup is very localized. It's inside a magnetic field. So the way these cold atom people do is they prepare this MOT in some ultra high vacuum, and then they let it fall under gravity, right? So that and then they study how they disperse and all those things. I have not thought about it, but our sample is very localized. So I have to see how we can. Maybe there is a way to simulate such effects in a different way. So I have not thought about it.
Okay. And one more thing. So did you, for example, if you remember Chiranjeev's that antiferromantic system, he could really see susceptibility and concurrence, how they were, concurrence was affecting susceptibility. Now here, for example, susceptibility is sudden death, concurrence, sudden death, those kind of behavior. Is it possible to observe?
Again, I don't know. Maybe it's interesting thing I should discuss with Chiranjeev and you, I think.
Yes.
Sure. Yeah.
I have two questions, so I don't know whether I have time.
Sure.
How effective, first of all, thank you for a very interesting and informative talk. And the question is how effectively one can generate or create known state, and with which effective number n? 3, 4, 5, 6,
So known states can be prepared very precisely and very efficiently. For example, this architecture, this is called star topology system. This is perfectly suitable for preparing known state. We have prepared known states. Recently, we have one is in archive now. So we have prepared known state of 15 qubits. In fact, we have prepared the known state of even larger qubits also. We have taken this 38 qubit system and we have prepared known states, which are also of this symmetry. So you see, preparing known state here, it requires just Hadamard and one CNOT. That's it. It prepares known state. The reason is the symmetry. Hadamard prepares superposition of the central qubit, and one CNOT is CNOT on all because of the symmetry. Okay, so you see now with just one Hadamard and one CNOT, you can prepare known state.
Thank you. Final question. Since this known state is very sensitive to perturbations, and then it will sense also undesired noise sources.
Exactly. So that is the exact question that is happening later in the solid state NMR. You see, known state is very sensitive, so that's why it is very good for sensing. At the same time, it is also sensitive for perturbation. So this perturbation, sensitivity to perturbation grows with the size. So now that's why we wanted to know what is the optimal size of the known state.
So my question is how we can distinguish whether we are sensing desired noise or desired signal from undesired one.
See, one way is, for example, if there is a way to cut off the sensing field. Then we can see what is the background signal. So that background signal is because of the perturbation. And now you bring the material that you want to sense.
Thank you.